So today we want to take a look at one more use of our variables. And what we're actually going to be looking at is we're going to be looking at graphing values. We've looked at the simple equations like a variable equals a number, like x equals 4. Graph that value would be quite simple. Go to the number line. We've used number lines several times before. And we've actually seen a couple of different ways of representing x equals 4 on the number line already. One of them, when we were working with negatives, integers, was that vector representation where we started at 0 and we went to 4 with that arrow, that vector. If we were going to represent a lot of values, though, that would get quite cluttered. So a simple way of representing a simple single value, if we're not going to be using it to mechanically combine it with anything else, is to just put a dot at that value. So we can just put a dot at 4. Well, that's if we're representing a single value like that. Sometimes we have to figure out what that value is. We might be given the equation ten equals 3x minus 2. We might be asked to solve it before we graph it. So we would add 2 to both sides to get 12 equals 3x. Then divide by 3 to get 4 equals x. The 4 equals x, or x equals 4, and we put that dot at the 4 still. Well, most of what we're concerned about for graphing is about relationships. If this were a college algebra course or an intermediate algebra course, we'd be looking at inequalities, having arrows or shaded areas on the graph. We're not going to worry about that so much for now. But what we are going to look at is what happens if we take our equations like this, 10 equals 3x minus 2, and we explore other equations that have the same form, that require the same steps to solve. We might have 16 equals 3x minus 2. If I go to solve that, the steps are going to be the exact same as what I just did. I'm going to add 2 to both sides to get 18 equals 3x. Then divide by 3. Get 6 equals x. Or I might have 22 equals 3x minus 2. Again, to solve that, I'm going to add 2 to both sides. 24 equals 3x. And I'm going to divide by 3 to get 8 equals x. In each of these equations, it was the exact same steps required to solve. Add 2, divide by 3. Add 2, divide by 3. Add 2, divide by 3. The reason for that is because the right side of this equation is exactly the same each time. So to get the variable, to get x by itself, we had to do the exact same steps to remove the pieces that were built onto it. This is what is referred to as a family of equations. And they can all be represented as simply y equals 3x minus 2. That represents all those equations and all the other families that go, all the other members of that family of equations that go with them. To express the solution to this, however, it's way more complicated. Each one of these pieces up here, let's take this first one. You can think of it as saying that I took y equals 10 and found that x equals 4. Well, we don't want to have to write that out like that every time, so we use an abbreviation. It looks like this, 410. It's called an ordered pair. And ordered because the order matters. The first number is always the x value.
Recording is on.
So we can just list the numbers rather than having to list the variables out. Now, unfortunately, this family of equations here, y equals 3x minus 2, is going to have an infinite number of those ordered pairs. No matter what value I chose for x, I could find a value for y that would make it true, or the other way around. If I chose a value for y, I could find a value for x that makes it true. So in order to express the solutions to that, we have to find some way to show an infinite number of solutions. Now first, we're going to go back to our graph here using these ordered pairs. To graph two numbers, 4, 10 is our ordered pair here. To do that on a single number line just doesn't work real well. One of the things that was tried once upon a time was to put the two numbers on there and link them together. Here's 4 and here's 10. But it's an ordered pair, so the link has to show which one comes first. So it has to have an arrowhead of some sort saying that we started at the 4, went to the 10. You can see how that would get very cluttered very quickly. Another thing that was tried was two number lines. So they would mark the 4 on the one number line, 10 on the next. They still had to have them linked because if we put any other pairs, ordered pairs out there, we'd have to know which ones went together. So again, that got cluttered rather quickly. Well, about 2,000 years ago, a mathematician by the name of René Descartes came up with something called the Cartesian coordinate system. Now, when you guys do any sort of CNC in the shop, you're going to use the Cartesian coordinate system. It's typically called the rectangular coordinate system. Because it really does, it starts at a beginning spot and works out in rectangular shells from there. For CNC, there is a second coordinate system. I don't believe we use it in the shop here at WITC. It's called a polar coordinate system. If you're doing a lot of circular features and certain fancy curves, the polar coordinate system works. It's just way quicker. You can switch the whole system over, and it's a little bit faster to program in some of those cases. But for the most part, locating features and doing things that are mostly straight lines, the rectangular system is a lot easier to use. So the way Descartes set up his system was he started out with a single number line as always. 0 in the middle, positive numbers going to the right, negative numbers going to the left as always, and refer to this number line as the x-axis. So that number line, that axis is going to be used to represent the values of the x value in that ordered pair. Then Descartes took a second number line and put it vertically through the 0 point of that first number line. This second number line Descartes called the x-axis. Positive numbers going up, negative numbers going down. And the common 0 point where the two axes crossed was called the origin. Called it the origin because that's where everything begins. Everything starts there at 0, 0 and works its way out. Now, I'm not going to insult you by putting a lot of points out here and having you name the coordinates of the points. I'm going to assume you can do that. I will do just 1 or 2 quick reviews here. For that point there, we read the x-axis first, which would be at 3. And then the y-axis, which would be 1. So that would be the point 3, 1. We read the x-axis first, then the y-axis. So back to that family of equations. Y equals 3x minus 2. To express the solution set, the infinitely many solutions to that, I start by just randomly picking a value for one of the variables and calculating what the other value has to be. In other words, finding individual solutions. Typically, it's way easier to pick a value for x and figure out what the value has to be for y. I'm just going to try a few values here. -2, 0, and +2 for x. And let's see what they give us as values for y. So if x is -2, y is 3 times x minus 2, so it'd be 3 times -2 minus 2. 3 times -2 is -6. -6 minus 2 is -8. So this gives us the ordered pair. When x is -2, y is -8. X is -2, y is 1, 2, 3, 4, 5, 6, 7, 8. So right about there is where that ordered pair would be plotted on our graph. Next, if x is 0, well then y is 3x minus 2, so 3 times 0 minus 2. Well, 3 times 0 is 0. Minus 2 is -2. Giving us the ordered pair when x is 0, y is -2. So 0, -2 is about there. X is 2. Y is 3x minus 2, so 3 times 2 minus 2. 3 times 2 is 6, minus 2 would be 4. So that gives us the ordered pair that when x is 2, y is 4. X is 2, y is 1, 2, 3, 4. Right there. Now, at this point, we can see from these 3 points that this forms a line on our graph, like that. So we can just draw that line through those 3 points. Now, I also happen to know from the form of the equation that just this was going to form a line. Otherwise, we may have been jumping to conclusions a little bit quickly here. We'll show some examples coming up as to where we might have to be a little careful with that. Well, let's first talk about what does that line represent? Well, that line represents every possible solution to the equation y equals 3x minus 2. If I look at this line here, if I pick a spot, like right here, I trace that down, that goes down to x equals 1. I trace that over, that goes over to y equals 1. So the coordinate of that point on the line is 1, 1. If I go back to my equation and I put 1 in for x and 1 in for y, 3 times 1 is 3 minus 2 is 1. 1 equals 1. That makes that equation true. That point on the line, the x and y coordinate of that point on the line, make the equation true. Also, we could have just picked a point, pick a value. Let's say we pick a value of x equals negative 1 here. I trace that down to the line here. And I trace it over, and I get y equals negative 5. If x is negative 1, is y negative 5? Well, I go back up here, put negative 1 in for x, negative 5 for y, and I see if that's true. 3 times negative 1 is negative 3, minus 2 is a negative 5. So that point, that coordinate of that point off my line, makes the equation true. Every point on that line, if I take its x and y coordinate, will make that equation true. Any x and y coordinate that makes the equation true will appear on the line. Every solution to that equation is represented by that line on the graph. Now, not every one of our equations is going to form a line on the graph. We might have y equals x squared minus 2x minus 3. Start out with our table again. I'm going to pick some values for x, negative 2, 0, and positive 2 again. And let's figure out if x is negative 2, what does y have to be? Well, if x is negative 2, y is negative 2 squared minus 2 times negative 2 minus 3. Negative 2 squared is a positive 4. Negative 2 times negative 2 is a positive 4. Minus 3. Well, 4 plus 4 is 8, minus 3 is 5. This gives us the ordered pair that when x is negative 2, y is 5. X is negative 2, y is 1, 2, 3, or 5. X is 0. Well, y would be 0 squared minus 2 times 0 minus 3. 0 squared is 0. Negative 2 times 0 is 0. 0 minus 3 is a negative 3. So this is giving us the ordered pair that when x is 0, y is negative 3. So we got 0, 1, 2, 3, negative 3. There's a point right there. Let's try 2 here. If x is 2, what's y have to be? Well, if x is 2, y is 2 squared Minus 2 times 2 minus 3. 2 squared is 4. Negative 2 times 2 is a negative 4. Minus 3. 4 minus 4 is 0. Minus 3 is negative 3. So that gives us the ordered pair that when x is 2, y is negative 3. So positive 2, negative 3 is right there. Well, pretty obvious that this does not form a line. Those 3 points do not line up at all. But what it does tell us is it gives us a chance to look at the graph and figure out where we need more information. First of all, I need more information between here, between those 2 points that have the same y value there. Looks like that's going to be at x equals 1. I need some more information over here. Probably like x equals 3. So I'm going to try x equals 1, x equals 3. See what I get for further information over here. So when x equals 1, y is going to be 1 squared minus 2 times 1 minus 3. 1 squared is 1. Negative 2 times 1 is negative 2. Minus 3. Well, 1 minus 2 is negative 1. Minus 3 is negative 4. That gives us the ordered pair that when x is 1, y is a negative 4. X is 1, y is negative 4 is a point right there. If x is 3, y is going to be 3 squared minus 2 times 3, 3. 3 squared is 9. Negative 2 times 3 is a negative 6. 9 minus 6 is 3. Minus 3 is 0. That gives us the ordered pair that when x is 3, y is 0. X is 3, y is 0 is right there. Well, looking at this, I would say, well, maybe I want to know what's going on right here at x equals negative 1. And one more step over here at x equals 4. X equals negative 1 and x equals positive 4. So if x is negative 1, this is negative 1 squared minus 2 times negative 1 minus 3. Well, negative 1 squared is 1. Negative 2 times negative 1 is a positive 2. Minus 3. Well, 1 plus 2 is 3. Minus 3 is 0. Gives me the ordered pair that when x is 0, or sorry, when x is negative 1, y is 0. That's a point right there. And if x is 4, y is 4 squared minus 2 times 4 minus 3. 4 squared is 16. Negative 2 times 4 is negative 8 minus 3. 16 minus 8 is 8 minus 3 is 5. Giving me the ordered pair when x is 4, y is 5. So over here, x is 4, y is 5. At this point, I feel I've got a pretty good idea what shape this makes. Looks like that. That shape actually has a name called a parabola. Typically, it's a shape that comes out when we have what we call a quadratic equation. In other words, an equation where x has a squared in it as its highest power on the variable. Now, the main point here is I started out with just a few points that I picked. X equals negative 1, x equals 0, and x equals negative 2, x equals 0, and x equals positive 2. I found the y values for each of those. I found the ordered pairs. I plotted them. but those first 3 points were nowhere near enough to have an idea of how to sketch out that graph. So I kept picking points, looking at the graph, figuring out where I needed more information, used the graph to pick more points for x, found the value for the y portion, the y coordinate based on that value of x, and I kept plotting points. Now, I probably plotted more points than I needed to graph this, but you get the picture. I can look at the graph and use it to figure out where do I need more information in order to figure out this graph. Now, I mentioned we have to be a little careful about the lines. I might have something like this. Y equals 4 minus x to the third power. So once again, I'm going to pick values for x and figure out what y has to be from them. And let's just stick with the -2, 0, and 2 again for x. If x is -2, y is 4 minus -2 to the third power. -2 to the third power is -8. So 4 minus -8 is a 12. Giving me the ordered pair -2, 12. So we get a point somewhere right about there. X is 0. Y equals 4 minus 0 to the third power. That's just 4. So the ordered pair is 0, 4. 0, 4 is right there. If x is 2, 4 minus 2 to the third power. Well, 2 to the third power is 8, so this will be 4 minus 8, which is -4. So that gives us 2, -4. 2, -4. Now, if I look at those points right now, it looks like it should be forming a line on the graph, because those points do form a straight line at this point. But I do have to be careful. Let's throw in some points in between here. Let's use x equals -1 and x equals +1. X equals -1. That would give me 4 minus -1 to the third power. Well, -1 to the third power is -1. So that's 4 minus -1, or a 5. Giving me -1, 5. -1, 5. Right there. Well, it does no longer look like a line. That point throws things off. Or if x is +1, this is 4 minus 1 to the third power. 1 to the third power is 1. 4 minus 1 is 4. Or 4 minus 1 is 3. Giving us the ordered pair when x is 1, y is 3. Got 1, 3 right there. So we get kind of a S-shaped curve, looks something like that. Technically, that's called a cubic curve. So for the remainder of this first hour in Blackboard, I put out there a worksheet for today. And that worksheet is 10 equations. I gave you some potential values to use for x in a table. Plot points, graph those equations. We'll give you the last 17 minutes here, the first hour, to work on it. We will start off next hour. We'll start talking about that worksheet, and we're going to use that worksheet to kick off our topic for the second hour. So it is out there in course information, week 12. So I'll stop recording so you guys can start working on it.